This is the best part. This is a lot of fun, I promise. Retrosynthetic analysis. Huge logic puzzle. But you got to know all your reactions. Got to know the language before you can play the game, right? So let's put together the reactions we've learned into a logic puzzle. So it's basically like engineering. Someone will come to you as a chemist and say, chemist, I need a drug that has this piece. Or you as the chemist might say, hey, I need a drug that has this piece because that drug will fit perfectly right there. Or it's similar to another drug that we know is hard to isolate in nature. So if we want this functionality incorporated into a larger molecule, how can we do that? Because it doesn't just exist like that. You have to have smaller pieces. So it's kind of like a Lego project. You have all the pieces you know exist. So in order to design a really nice Lego set that someone asks you to do, you have to know all the pieces that are available. You have to know all the pieces that are accessible here too. What functional groups can you turn something into? What functional groups can you start with? And most of the time it'll tell you as a problem what you need to kind of start with as a guideline. You know, in the professional world, you'd have a better idea by then about what's available commercially. But this one will say, hey, starting from this, get to here. Okay, so this is available. We can buy this in bulk and cheap, but we want to make this. So lots of key things to look for. We talked about regiochemistry. We talked about stereochemistry. We always pay attention to that. We can look at carbon counts for the regio, right, for where everything went. We also think about the functional groups that we did. Like, I even use those names, that vocabulary, because you know, if you're doing a Lego, you might say, I need a double peg or a quadruple peg or a square versus a rectangle. You would actually verbalize what you need. So it helps to verbalize and write down and connect the words with the structure. So what did we have? What is made here? Well, the only functional group that we could discuss is a dihalide. So dihalide. That's the functional group. What's the relationship of the dihalide? The two halogens are anti to each other. That addresses stereochemistry. So I'm looking at stereochemistry is anti. I'm looking at functional group is dihalide. I'm also looking at regio. They're vicinal, right? Or 1, 2. I made a vicinal dihalide with anti-relationship. Okay, so because this is more than one step, I might get stumped if I try to do this. Say, what do I need to do next in order to go here? It might be more helpful to think backwards. So if someone had handed you a complicated Lego piece, you might, or construction, you might actually think about what project you made before it, right? What was the base? What did the base look like, or the foundation? We wouldn't just jump from a simple Lego to a really complex build, right? So we're going to, likewise here, we're not going to start with the simplest thing and try to end up here. We're going to do both maneuvers. We're going to say we could go forward if we know what to do. We can also think backwards, which makes a lot more sense, but it's hard to train your brain to do that at first. There's a special arrow for that. There's a lot of arrows in chemistry, right? There's equilibrium arrows, there's resonance arrows, there's curly arrows, there's reaction arrows, and now you're getting this block arrow, which is the retrosynthetic arrow. It has a meaning. When you use that block arrow, which to draw it, you don't have to take your time to draw it all perfectly like that. Usually hand drawn, it looks like this. So that's the block arrow. That means you are going backward one step. You are not doing that reaction. You are thinking backwards. This is retrosynthetic analysis. You are thinking about it. You're making your plan. Thinking back one step. Students, countless students will think we're doing a reaction here, that we are going to get rid of these and turn it into something else. No, this is our final target. So this is our target. We use that word. Sometimes it's even abbreviated TM, target molecule. This is SM. This is our starting material. We have to end on that. We are not reacting that. We have to make that. What did we make a vicinal dihalide from that's anti? There's only one functional group possible. To have a 1-2 relationship between two halogens and have them anti, we had to have an alkene right there. See how thinking backwards actually simplifies it a lot? Because we wouldn't have known that going forward. That had to be an alkene, right? So I'm going to write that here. Anti-vicinal dihalide must have been an alkene before, right? Okay, we're not home yet. Like I said, it's multi-step synthesis. But I always check, am I done yet? Nope, those don't match. When those match, you're done. Okay, what could I have had to make an alkene? I reacted the alkene to get that, but I had to get here to somehow make an alkene. What makes an alkene? Elimination. Had to do an elimination reaction. So therefore, I need a leaving group. So I'm going to write that here. For my next step, my next reasoning, working backward, I'm going to say alkenes are made via, we're going to stick to second order in synthesis because carbocations just complicate it a lot. So you don't usually account for those, usually avoid carbocation paths in retrosynthetic analysis. So we're going to stick to E2. So what would help me? That would mean that one of these two carbons needs to have a leaving group. Since it's symmetric, it actually doesn't matter which one I pick. And I'm just going to pick chlorine to be my leaving group because it's not bromine and I don't want to confuse them later. So this would have made that alkene, right? So all that time that we've sometimes predicted the missing starting material, that's kind of training for this thought process. We're still not there, but it's starting to look similar to it. So notice how we have a methyl-methyl single bond, right? But we have the leaving group in the wrong spot. We need to somehow have a bromine there that when it reacted, we were able to install a chlorine here. How do we put in a halogen? And then furthermore, let's draw everything out just to note. So there's H there, and H there, and H there. We have an H here. So we're actually missing, this H is not here. We have a chlorine there instead. And this H shouldn't be there. How do we put in a halogen? One halogen, monohalogenation. Monohalogenation, not dihalogenation. Alkene reaction once again. HX is one alkene. XX is one halogen. HX is one halogen. XX is two halogens. So where was the alkene? So I'm going to write that here. Monochlorine. I'll write it in a different color. Monochlorine came from alkene. Okay, what would that alkene have to look like? Well, it could have been here. That would give us a monochlorine, but then we just made that, we just got back to that again, and that doesn't help. What about if we have the alkene here? The chlorine would go there because it's Markovnikov. And if the alkene was here, that gets us closer to having functionality right there that we need it for getting close to the starting material. I like that idea. Let's do that one. Okay, we don't match the starting material yet, but could this alkene be made from that? Well, it's a halogen, and we made an alkene. So it's a leaving group that turned into an alkene, so that was E2. So yes, that brought us back. So that was the retrosynthesis. That was not the forward synthesis. That's the final answer. That's the problem-solving strategy because, hey, I'm going to acknowledge that's hard. You need a strategy. You need something to help you solve the problem. That's what retrosynthesis is for. Believe it or not, it's to help you get to the forward synthesis because that's too overwhelming to just start from nowhere. It's a problem-solving technique. The forward synthesis does the opposite. It starts with the starting material right there. So we write that out. And then we add the reagents necessary for each of our intermediates. So to make that alkene, I'm going to do an elimination. Let's do NaOET, like we've done many times. Okay, so now we're at our first alkene. Now we need to get to our monochlorinated product, HCl. And then remember that is Markovnikov, so it goes over there. Then we made another alkene. Elimination again, NaOET. Now we have an alkene between the two methyls, which means we're ready to do bromination at our CCl4. And one of the two enantiomers matches the product. Of course, we can't help but form the other one. So I'm only going to write the one that we cared to get in the box. But of course, we will make some of the other. And that's okay, because there are ways to separate them, even though it's not easy. Okay, kind of fun, right? So we proved that we could make that. Notice this is actually going to be a common sequence in some of the retrosynthetic analysis. We move the double bond over. It's called move the double bond over strategy. Some actually explicitly call it that. Move. That helps add functionality to an area of the ring where it didn't look like there would be any. For example, it looked like all our functionality was stuck between these two during our retrosynthetic analysis, but we saw we needed a third carbon to be at play there. So we employ the sequential addition of leaving group, elimination, additional leaving group, elimination to move the double bond over based on whether it prefers Markovnikov or not. So do you see how here it's not the same spot as it was there? Addition, elimination, changed where the double bond was. Okay, well, that is the best place to culminate. We will be doing synthetic analysis for every chapter with the new reactions we learn. But guess what? They're going to rely on old reactions. For example, elimination is not explicitly part of this chapter, but we cannot do a synthesis without using the elimination here. So they keep popping up. So make sure you get the new ones down. I recommend writing it up in sort of a summary chart. Okay, and we'll do that together too for the first few, but I want you to try summarizing it in one sheet on your own, all those reactions, so that when you encounter your next retrosynthetic problem, you can kind of quickly reference them so that you're ready to go. Okay, it takes time to learn those as well. Have fun, go write your summary sheet, and then embark on some of those problems.